Greetings magicians, Loic here for a tutorial. Today we're gonna learn how to create a pendulum wave in Houdini. A pendulum wave is a science experiment where several pendulums of different length oscillate. As they have different length, their period of oscillation will not be the same and interesting patterns will appear. First, I'm gonna quickly explain what are the math and physics of this experiment. As I'm not a math teacher, it will be pretty basic. Then we will jump right into Houdini and begin to work with an attribute wrangle where we will be creating the strings. Right after that, we're gonna simulate the system with a Vellum solver. Then we will add the spheres at the end of the strings with a copy to points. Finally, we're gonna convert this whole system into an HDA just for fun. So let's not wait any longer and begin! Before beginning this project, I had to search for references and mathematical explanations. Luckily, I found both on that awesome video from that awesome guy NightHawkInLight, and it's how to make a pendulum wave. I will give you the link in the description. I definitely advise you to watch that video, you'll understand my tutorial better, I think, but if you don't want to watch it, it doesn't matter, I'll try to explain as best as I can. So let's scroll down a bit, and here are some measurements. We will be using them just to make sure that we did the right thing inside of Houdini. Let's click on that link. Scroll down a bit, go to the going further part, and two things are important here for us. First, we have to know that the period of an ideal pendulum depends only on its length. So in order to create asynchronous patterns, as you could see at the beginning of this video, we will have to mess with the length. And that's exactly what this formula is for. It's gonna give us the length of a pendulum depending on these variables. So we're only gonna give the initial length of the pendulum, and every other length will be calculated. So let's do it right away in our favorite software, Houdini. Let's create a new project called Pendulum Wave. Let's copy that, accept, save it right away, and accept. Let's drop down a GeoNode, dive in it, create an attribute wrangle, and rename it. So it's gonna create the strings, so that's what it's gonna do. So we don't have any points, primitive or vertices, so we have to set to run over detail. What I'm gonna do first is to type the formula that we just saw. So it was equal to G times 2 pi, it was Tmax divided by 2 pi times K plus N plus 1, and it was at the power of 2. So that's good. As I told you, we're gonna create the initial length, and from that initial length, we're gonna calculate every other length. I mean, we're not gonna calculate it, but Houdini will. Well, so let's create a float called init L for initial length, and I want to set it to 0.3. Again, I'm taking the values that NightHawkInLight gave, just to be sure that we did the right thing, and then we're gonna modify that. So 230 millimeters is equal to 0.23 meters. Let's create our float G, our gravitational constant. So Newton told us that it was 9.81 meters second squared. Let's create another float for Tmax. Tmax, if we go back to the description here, is equal to the overall cycle seconds. The overall cycle length in seconds. So if we want it to last longer, we're gonna put a higher value. But for now, it's only gonna be equal to 24. I want to create a float for pi as well. Houdini understands pi, but written like this. But I'm a bit lazy, so I want to spare one character. So I'm gonna write it like that. K will be a bit different. So I'm just gonna type for now our integer, our basic counter iteration n. It will start at 1, obviously, because the first length is when n is equal to 1. N is equal to 0, it would be a value that doesn't exist in the pendulum. So it will start at 1 and then go to 2, 3, 4, and so on and so on. So we have every variables that we need, but we don't know what is k. K is the number of cycles the whole apparatus goes through before repeating the pattern. Actually, we don't know what it is. So that's the only variable we don't have. so we can calculate it when L is equal to 1. When N is equal to 1, so L1 for initial length. So what I did here was I did the calculation to put K outside of this equation. So the result is that. I'm gonna type that into Houdini and I'm gonna check if this is correct or not. So you have to believe me for now, but I'm gonna make sure that it is correct. So it was Tmax divided by square root of L divided by G times 2 times pi, and the whole thing was minus you subtract n and 1. And this was at the power of 2. No, it's not at the power of 2, sorry, it was above that it was. So now I think it's great. So let's create an attribute called test that will be equal to K. Actually, this is not L, this is init L, so I'm going to replace that. Click outside, so it calculates. Look into the geometry spreadsheet, go into the detail tab, and it's equal to 22.9, and it's about what NightHawkInLight had. So I'm not messing with you, it's the correct value, I did the calculation right. So K is equal to about 23, so that's what we have. We can delete K and type our L formula the right way. So let's create another variable called L, and it's equal to G times Tmax divided by 2 pi, 2 times pi times K plus N plus 1. And this is at the power of 2. So for the power of 2, what you have to do is use this function. It's pow. The first argument will be what you want to put at the power of something. So we want to put this at the power of 2. So let's check if this is correct, again, with a test variable that I'm going to set to be equal to L. So let's click outside, and actually this is not good. Yeah, this is because I want this to be I want Tmax to be divided by the entire thing and not just by 2. But it's a bit weird how Houdini does the calculation. So yeah, now it's equal to 0.23. That's not a big surprise because we are calculating L1, because here N is equal to 1, so it's L1, so it's our initial length. But if I replace manually N by 2, for example, so the second length, if I click outside, it's 0.21. And if I go back to the measurements, this is about it. I'm going to do it for N is equal to 3. It's equal to 0.19. It's about it. So I think we have the right calculation here. So I'm going to delete that and put N back into the equation. I can erase that for now because we have our formula written the right way here. So now we are pretty well set to create the geometry. Create geo. Let's start by creating the points. First, let me show you something. I draw this little diagram to be sure that we are on the same page. It's the pendulum seen from the right or the left, from the side. So for each pendulum, we will need 3 points and 2 variables. The spacing variables that will be the same for each new point, and our length, which will be calculated for every loop. So 3 points, 2 variables, one that we don't have for now, but we're going to create it. So it's a float down for the spacing that I'm going to call S, and which will be equal to 0.25 for now. So let's create the points. So our PT1, you have to create a point with this function. So add point. First you have to give where you want to create the points. So 0, that means on this node. We want to create this point on this node. And we want to create this point on the auric vector. But we don't have an auric vector, so let's create it. For now, I want it to be equal to 0. And if I click outside now, you can see here, there's a point created. We now have 1 point. Perfect. Let's create the second point. So we're going to use the same function on the same node, but I want to change the position where it be created. So we want it to be created on the nString vector. So let's call and let's create and initialize that vector, and I want it to be equal to orig for now. It will be useful when we put this inside a loop, and if we want to change the orig vector, because we want the nString to be based on the orig vector. Now, for the nString, it's here. We want to subtract s and l out of the orig vector. So let's do it right away. We want nString.y to be subtracted by l. We want to subtract l out of nString, and we want to subtract z. Oh, sorry. nString, we want to subtract out of z, we want to subtract s. So now, if I click outside of this node, we have our point. Let me go to the right viewport. Let's go here. I'm gonna increase the size of these points for you to see. And here we have our 2 points we can see in the geometry spreadsheet at the right coordinates, 0.23, so our first length, and our basic variable for the spacing. So that's perfect. Let's create the third and last point. I want to create a point again in this node, and I want to put it in the orig vector. I didn't want to create another variable. I just want to create 2 and update them. So let me update the orig vector. I'm going to show you what I'm planning to do. So we have the orig vector just here. What we want to do is to take the nString z coordinates. So from there we're going to go there, but we are not going to take the y position. So we're going to go here and then subtract s again. So we're going to go there. So let's do it. orig.z is equal to nString.z. If I click outside, oh, there is a problem here. If I click outside, you can see that it's right above the nString. And now I want to subtract s, and it would be pretty good. We have our point set, so that's perfect. Let's create a primitive now. So let's call it prim, because it's just gonna be 1 prim per loop. So we're gonna use almost the same function. We're gonna add a prim on this node, and it's gonna be a primitive of a polyline type. So it's gonna be an open line, but it's not gonna be a polygon which will be closed. It's gonna be an open polygon, if you may. If I click outside, nothing happens, except that it has created something here. But we don't see anything in the viewport. That's because we don't say that the primitive should be linked with this 3 points. So that's what we're gonna do with the vertex. So let's create a vert1 so we're gonna use the add vertex function. We're gonna add a vertex on that node, sorry. We want to link the primitive with the pt number 1. And if I click outside again, you can see this point has disappeared. And here we have our first vertex created. So that's perfect. Let's create two others. Actually, let me create just another one so you can see what it does step by step. Vert12. Vert2, and it has created a line between the point number 1 and the point number 2. So if I do that with the number 3, we should have our strings done. And it has. So we have our string here. We are almost set for the loop. I just want to create some groups. It will not be useful for this node, but for the Vellum solver, we want to pin some points, so we'll have to create some groups. And for the copy to points, we want to target the bottom point to be the position where the spheres are going to be created. So let's do it. We want to use the function add point group, and we want to add a point group on that node. We want to add a group that would be called pin. The PT1 number 1 will be in that group, and it will be equal to 1. If it will be equal to 0, that means it's not in that group. And we want to set the value for this point. Now I'm gonna copy it once, twice, and I want the point number 2 and the point number 3 to be in a group, but the point number 2, as I told you, will be in a group that I'm gonna call bottom, because it's the bottom, I mean. So let's click outside, go to our geometry spreadsheet for the points, and you can see that we have our points and the groups are well set. For the first one, it's the group pin that we're on. The second one is the bottom, and the third one is in the pin group. Now we can start by creating a loop. Lop. Okay, let's initialize the loop, the for loop. So we will take our counter, iteration counter n, starting at 1 again. As we already initialize it here, we don't have to do it inside of the loop, but we have to say that we want to take that variable. As long as n is lower or equal to a channel integer that would be called iterations, we want the loop to occur, and at the end of each loop we want to add 1 to n. So let me close the loop, put everything that's in between, indent that. Before watching what it has done, we want to put the vector orig outside of this loop, because we don't want to be set at 0 at the beginning of each loop, because it doesn't have any points in doing that, because the pendulum will be on the same place, on the same position. So and we want to do, let's click outside. Yeah, I want to click on that button and put, for example, 8 iterations, and here we have our 8 iterations. But my bad, I didn't put L inside of the loop, so n here, you can see n is equal to this length will not change. It will be calculated once, but it doesn't change depending on n. Whereas if I put it inside of the loop, n will be set to 1 for the first loop, the second loop will be equal to 2, and so on and so on. So let's click outside, and now it should be good. And it is. We can verify, check the measurements. So 23, 21, 19, 18, 23, 21, 19, 18. So we have our formula is well written. Perfect. Now that we know that we have the right thing, we can control what we want to control. So let's create a channel float for the initial length. Let's not do that with the gravitational constant. I'm not sure Newton will agree on that, so let's leave it as it is. Tmax is going to be controllable too, and it's going to stay at 1. Our spacing variables could be modified too, and as well as our orig, pendulum orig. So let me call it pendulum origin. I'm just going to put an underscore here. Save that, click on this, and put our values back to what they were before. Our spacing should be equal to 0.25, and our pendulum origin is, for now is okay. I'm going to go to our perspective viewport, and just make sure that this is okay. And yeah, it is. So, awesome. We have our strings done. So, let's go in there. Actually, what we could do is I can show you that the iteration indeed they work. The initial length, everything moves. Tmax, it changes the slope. Actually, you could see as a diagram, it's a bit of a slope, and the more you put it higher, the more it becomes to a linear shape. And our spacing, obviously. So I'm gonna put it back to what it was. Tmax 24.0. All right, let me put a transform node after, and I'm gonna name it rotation because we're gonna rotate these strings. So we want to rotate them on the z-axis. So I'm gonna put 35 for now. And when the gravitation comes into place, the strings will move. It will give a momentum and will have some motion. Let me put a null here. Actually, I prefer that color. Yeah, my null is a bit weird. For example, if you want to set a color to be the default of a node, you can click and drag that color onto a node. For example, I'm doing this with that yellow goldish color, and I'm creating another node, and it has taken this color, and it's the same with the shapes. So control click, and it will change the default of this node. So let me put that back. So out strings source, big source. So yeah. Now, what we want to do is put that inside of a Vellum solver. But first, we have to configure the constraints of it. So let me... okay, I'm taking the Vellum constraint node. I'm going to the constraint type, and I'm setting it to be a string. And as I told you before, we want it to pin to animation, pin the points. So I'm gonna pin the points of the group pin, obviously. So that's the only thing we have to do on the Vellum constraint node. What we want to do now is put our Vellum solver. So in that solver, we want to modify the substeps. We want to put a higher value, for example 4 will be okay. Decrease that by 10%. It will just be equal to 10, and this will be equal to 1. We won't have any collision between the strings actually, so we can decrease that. And the forces. If you want to do something that will be similar to something in the vacuum, you could uncheck the wind, so there is no friction. But if you want to be a bit more realistic, you could put something like, as our scale of the scene is really small, we can put something to like 0.01 or maybe 5. I'm gonna stick with 5 for now. And we're gonna see what it does. So I'm gonna go in front of our pendulums, our strings, and I'm gonna press Alt F. So I created a shortcut for launching the flipbook. So if you don't know how to do it, you go in the Edit tab, you go to Hotkeys, you type what you're searching for example, flipbook. And here you see launch flipbook render. You click onto it, and here you can see Alt F is my shortcut for that. So Alt F and start. Let's see what it did. As you can see, we have our motion here. So it seems pretty good. Actually, let me check the real-time toggle and put some more frames after that, so we'll be able to see the entire cycle. So starting after 24 seconds, because our Tmax is 24 seconds, it should be so after that point, the patterns will repeat. And actually, if you put no friction, it will repeat for eternity. So that's not what we want, but actually, that's maybe what you want, but that's not what I want. I want to do something a bit more realistic. So, yeah. It looks good. You can see that the amplitude decreases, so it's due to our friction. But if you want to have less impact on the amplitude of the pendulums, you can decrease the wind drag here. So we have our motion, and here we are. You can see, I think it's about, yeah, it's about here. You can see that here, it seems like it's the beginning of this, but at the other, on the other side. But if you go here, this is about 600 frames. So I think it's about 24 seconds, actually. 24 seconds, yeah, let's calculate that. 24 times 24, yeah. It's 576, so it's a bit, it's almost that. And it's because of calculations and because we're starting from there. And yeah, but the math of it are pretty well respected. So let's close that, put a null at the end of it, rename it out strings sim. And now we can move on to the sphere part. So let's create a sphere, template that, and you can see it's way too big. So let's put 0.01. It should be great. I'm gonna set it to be a polygon, up the frequency a bit. But as we're gonna be a bit far from the strings, we don't have to increase the frequency that much. I'm gonna create a copy the points, and we want to copy the spheres. And here you can see the target's points to copy to. So we want to copy the points, to copy the spheres on our bottom group. So that's what we are created. We created this group inside of the attribute triangle. So let's go back to the copy the points, and we want to uncheck the transfer using point orientation. Let's visualize that, and we can see here our spheres are well placed. We are almost done here. What we want to do is first create a null just for organization's sake and say that this is our spheres. Oh, sorry, I'm gonna take the same. And you can see here, if I uncheck show guide geometry, you can think that it's not only the spheres, but it is. It's just we had the guide geometry here. So if we uncheck that, we indeed have only our spheres. But what I want to do now is put a polywire after the strings, so they have a bit more shape. So we're gonna decrease that to 0.001, and if you zoom in a bit, there is a needly thing, weird shit going on here. So you can either decrease the smooth point or decrease the joint scale. So if I put that back, you can see that by decreasing the joint scale, it decreases this needly thing, but I think this is more efficient, the smooth point. And as we are going to be a bit far from the strings, we're not going to be needing some smoothing or stuff. So that's about it. Let's create a null, and it's going to be called out strings geo sim. Actually, we could say sim geo. Yeah. Let's create a merge and merge these two nodes together, and at the end of it we can put a null and name it out pendulum. What a joy to finish this project. So this is completed. Now, as I promised you, we are gonna create an HDA. So if you already know how to do it and you don't want to watch it, so that's about it. I think I'm not gonna show you anything you need to know after that. But for those who want to stick with me, let's do it. So let's select everything, go to Actions, create a subnet. So we're gonna create a subnet. We're gonna call it Pendulum Waves. And now what I want to do is right-click on it, create a digital asset, and I'm gonna name it Pendulum Wave Tutorial. Yeah, this is a pretty name actually. I love it. So we are creating a an asset here. What I want to do is change my custom my desktop to a technical custom, so you would see better, but you don't have to do it. What is handy here is that this panel is linked to this one, and this one is linked to this one. So I can go onto my pendulum wave, and I can go inside of it. So I'm seeing here what I'm gonna change. Actually, I'm gonna explain to you. Here what we want to do is create some parameters. For example, if I create a parameter, a float parameter here, you can see, and I have to apply that. It's gonna appear here. So from that, if we link this value to this one, we would be able to modify every node that we want from that place. So this is what an HDA is handy for. It's handy because of that. So what I want to do is create an integer variables, because we want to operate on our iterations. So there are integers. Then we need 1 float, 2 float, 3 floats, and a pendulum origin, which would be a vector, float vector 3. So 1 float, 2 floats, 3 floats, and a vector float. I'm also gonna add a separator here and add another float for the rotation. So yeah, I'm just gonna expand that a bit. It's gonna be iterations. I want to set its range to be from 0 to 50. Let's get crazy. Our parameter would be initial length. So init length, initial length from 0 to 1 meter. I think it's big enough. Our Tmax, still the best name on earth, so I'm gonna leave it as it is. Tmax 0 from 0 to 50. What about spacing? Let's name it spacing first. And 0 to 1 meter, it's big enough. It's way too big, maybe. I think we could, well, let's leave it like that. And this would be our pendulum origin, but I'm gonna call it orig here and pendulum origin. And we don't have to set any range. Our rotation would be rot for rotation and rotation for rotation, and the range from -50 to 50. I think it could be great. So I'm hitting apply here and accept, and then I'm gonna link this. I'm gonna copy this parameter and link it to the to what it corresponds to. So let me do that for the others, and we will be done, my friends. Parameter pendulum origin, and here the rotation, copy parameter and paste it here. Yeah, here. Right, that's perfect. So let's now put it to what it was. Initial length 24.0, spacing 0, and 35. And now I think we have our pendulum wave done here. So you can see everything works just fine. Actually, this is not good at all. I think you could go to the edit parameter interface, go to our spacing. Actually, I should go to the assets and go to the edit asset properties. I'm gonna go to the spacing and decrease that to, yeah, maybe 0.1. Apply, go, and yeah, we have a bit more control. We can be a bit more precise on that. And our pendulum origin works too, and as well as our rotation. Oh, there is a problem with the rotation. I think we should do something with the transform node. Actually, what we should, or we can rotate inside of the attribute triangle. Actually, let me look at it and I'll be back in a second. Okay, so what I realized here was that changing the position inside of this node was not very handy if we wanted to change the rotation outside of the node. Actually, what we could do is to change the rotation inside of the attribute triangle, and then after modify the position. But actually, what you can see that this is the node we created together. So we have our pendulum origin here, and what I did was adding these two nodes, actually 3 nodes, because we had our rotation here. So I'm gonna put back what we had before. So with the changing the pendulum origin, it does something crazy. Actually, if we put back to what it was, it's okay, as long as you don't change the pendulum origin. But for example, if I change that, you can see that it gets crazy. It gets crazy. So what we need to do is to take the strings, put it back to the origin. So thanks to we go to that node, and we can click to move centroid to origin. But what I'm taking is the centroid of this node. Then what I did was subtracting the half of the y size, so we have our pinpoints on the z axis, and then I can rotate, and then I'm putting back the translation that we had here. So you can see this is pretty tedious. And what we can do here instead, I just put it back to 0, 0, 0, so we're not changing that. We're we're doing our rotation here, and then putting the transform of that node. So if we're changing the transform on the HDA, it changes this one and this one. So you can see they are the same. If I take this one, go back through here, so we have our transformation here and here as well. So we have the same results, but here it's really more efficient and quicker. You can see here there are some nodes, you have to put something in the some other function, so it's not easy. So let's take this inputs, so this one. So that's it, guys. You can go there. Actually, you have to visualize that. If we get closer, actually, I'm gonna go back to 0, 0, 0. It was a bit more easy for me to look in the scene. So I'm gonna go back to my previous iterations. What the value was, this was that. Initial length, iteration, spacing, we have what we want, and we want to be 35. If I go in front of it, launch a flipbook, and I think I'm gonna tell you, say goodbye on that beautiful video, beautiful flipbook, and I hope to see you soon. This was my first tutorial, so I hope you learned something, and I hope my pronunciation was not so bad.
Maybe sometimes I was too fast or too slow on some notions, so please leave me a comment. I would love to hear from you and have your feedbacks. And if ever you render this pendulum or improve the HDA, it would mean a lot if you would send it to me. So, bye and see you soon.